SpongeJet distributors have performed a couple of applications on the towers for remedial work, and we'll go into one of those case studies shortly into the presentation. SpongeJet believe there is an efficiency gain by sponge blasting the turbine rotors and diaphragms. When it's put back into surface, there is less drag and it's free of contaminants, and 1% efficiency increase can relate to millions of dollars. The reason we're showing these turbine case studies is to empower you with information that you can pass on to your clients. Not only will you feel more comfortable about discussing the case studies, they will feel more comfortable that you have the basic knowledge about what needs to be performed. Remember, we're not trying to be the expert, we are not the contractor, but our equipment and media has been used and performed these applications on hundreds of times around the world with outstanding success. At the start of the case studies, you will find a project number up in the top left-hand corner. This is how we search for the case studies and our history file, in our history file and industry-related files. If any of you want a copy of the case study or discuss them at question time, please record the number or the tile number, and I can go back to it after this webinar. If it's after the webinar and you want a case study, if you make a request to Natalie will search the G drive and make sure that you receive an electronic copy. All of the case studies that you're about to see are available on the G drive in the SpongeJet library and the case history file. These that I'm showing you are the reduced versions of what's available. It is not the actual case study because we've had to reduce them to put it into this time frame. As we are limited in time today, we're not going to go through each tile and discuss the information that you're seeing, but inform you about the important information so you can look at the case study in more detail after the webinar. So what's important here? Loy Yang Power Station is the largest power station. Both Loy Yang A and B combined produce 50% of all Victorians' power needs. A self-sufficient open-cut coal mine producing 30 million tonnes per annum. That's 82,000 tonnes of coal to burn daily. How did this job come to fruition? To Loy Yang engineers and project managers about the benefits of SpongeJet many years ago. We arranged a demo at Kilsyth head office and invited them to bring some components and pieces for us to blast. The trial went exceptionally well. Loy Yang then arranged a side-by-side blast against ilmenite, which was the specified process of the turbine by the turbine owners, Hitachi. Although slightly slower, we finished with amazing. The finish was amazing. We could see the shiny exposed metal for the first time, and you can't get that from ilmenite. And from that moment onwards, this was the way forward for Hitachi. Hitachi specified sponge blasting and the sponge blasting cleaning process for NDT inspection and the removal of magnetite and scale. It's important to mention that there is no metal loss from this process. We do not profile the turbine blades or shafts or the diaphragms. It's strictly a blast cleaning process. Components usually get lowered into by crane into a prefab portable room or a habitat that's built around them. You can see that the burnt scale and magnetite on the before shot, if you look closely at the photograph there on the bottom. And this is how the diaphragms look after they've been blasted. Clean, white metal. The casings have to be blast cleaned to allow for NDT inspection on all the stress points and where the bolts go. A stress point is an angle, a curve, anywhere where there's not a straight line with the casing. The inspection process after blasting with sponge media is a lot cleaner than you would have as a surface cleanliness with ilmenite. The turbine rotor surface looks like new. as it's turned back to white metal. The media used varies according to the desired finish or requirements or specification. 62 bags were used in total, some 802 kilograms. The project was allocated 10 days based on the previous application times, which would have been within the night. SpongeJet finished the project in 7 days. That's 30% saving in time and labour, not to mention the added cost of bringing the plant back online earlier. It's a fantastic outcome. Project 930. The media used on this application was 320 and 320 DG, a total of 84 bags, some 764 kilograms. This is an Alstom turbine refurbishment, and it was craned next to the turbine and with a scaffold built habitat built around it. That scaffold is then built with poly-welded to cocoon the rotor inside to create 100% containment. A separate access room with a zipper is usually in place, and it's a perfect setup. They also installed an inlet vent and extraction point to allow negative air environment to create 12 cubic metres per minute. Engineers could work on other components while blasting was in progress. Inside the habitat is very clean, and there will be no escape of media, no media loss, and no dust outside of the habitat.
Right.
So the project is being cleaned, blasted in a sensitive area where there's equipment that is open and exposed, and the last thing they want is dust. Pictures are a simple way to explain things and how they're set up. In the top left is the inside of the access room, and the top right is the blasting in process. Another angle of the habitat showing the floor welded in. Inspections can be performed instantly. Other processes can wait up to 1 hour, even a whole day, for the dust to settle due to the airborne contaminants and exposure that might be to the inspectors. The blasting continues. Last minute check over. The casing is static, it can't be removed, and all blast cleaning is performed in situ. Then a negative air room or habitat is constructed over the fixed casing to be able to blast it. This is inside the habitat, the casing finished and clean. Bolts, plates, spacers are all taken to other locations off-site or into the workshop where they can be blast cleaned. It's not necessary to do them inside the habitat or on the floor. This is the concept that we actually sell to the plant owners. It's clean, efficient and cost effective. Project 907, another Alstom turbine, also performed in the same way, just a different country. Once again, to blast clean and remove the magnetite buildup. Plant owners hate things leaving site. They prefer to control it on site than they have control over the processes that are happening. It speeds up any downtime and also has less damage control. Again, blasting in a habitat in a poly-welded encapsulation. This allows for a dust-free passage in and out. And 320 and 320 DG were used on this particular process. I don't have any volumes, so occasionally if they don't put them on the case studies, we don't know what they would have used. The outcome of this project is that it took 4 days of 24-hour shifts to complete the rotor blasting and associated parts. The reason it performed this in application quicker, 4 days compared to 7, is that they used 3 200 HP blast units. We don't have the 200s in Australia. They're only built for Europe, but 3 100s or a couple of 400s would be the same application. Project 855, Taiwanese incinerator power plant suffering from iron oxide buildup from long-term high temperature operation. The objective is to perform NDT inspection. I've noted that there is that they use 120 and 220 on this particular application, depending on the sections that they need to blast on the turbine and diaphragms. I still recommend that 220 and 320 be used in place of the 120 and 220. A heavy see-through plastic habitat was constructed to perform the blasting. The before and after shots, always needed to build a good case study. 16 bags of media were used on the turbine and rotor and parts. That's 227 kilograms of media to perform the turbine, rotor and diaphragm blast cleaning. Note the calculation of media consumed was 6.3 kilos per square metre. Project 322, Westinghouse turbine set for refurbishment with bearings and seals that need to be replaced. While it's out, the rotor and fins will undergo a blast cleaning process. Suffering from the usual problems, this project was conducted on the powerhouse floor, again inside a welded plastic wrap habitat. The media used was 220 and 320, and it was a blended mix. This is the first case study that has pointed out the removal rate of 5.5 metres per hour on a job that involved some 158 square metres. To further those calculations, which I had done, that's 28.72 hours of blast time to blast the 158 square metres. The highlighted section is a great selling point. The contractor cut or reduced the shutdown time by 60%, brought it back from 30 days back to 10 days. Project 870, boiling water reactor. Turbine rotor blasting for NDT inspection, or NDE, which is non-destructive examination, both the same process. The habitat is not as elaborate as the other ones that we've seen. They've just used some tarp sections. The diaphragms were suffering from iron oxide scale buildup. This is just a picture of the blast cleaning in process on the diaphragms. Before and after shots of the rotor blades and the shaft. Another key factor is the waste compared to other abrasive blasting processes like ilmenite and garnet. SpongeJet has at least 10 times less waste. No real dust issues at all in comparison with the other blasting applications of garnet and ilmenite. The outcome of this project was the GE inspectors saved 2 shifts because there was no airborne dust. Typically, they would have to wait 24 hours before entry and inspection to the habitat. Some of the key items to point out to your customers are, and you might want to make some notes of these, that the sponge blasting process will not damage the turbine rotors and diaphragms. All surface contaminants will be removed, will not damage leading edges of the fins and blades, no damage to the journals and the seals, no metal loss, instantly readies the surface for NDT inspection or NPT or NDE, no downtime waiting for dust to settle. Inspectors can have instant access to the habitat. All processes can be performed on site. Nothing has to be transported away. It's cost effective compared to all other methods. Project 938. Pacific Hydro are the owners of the wind farm at Clements Gap, about 20 minutes out of Port Pirie in South Australia. Contract Resources asked if we could quote them on the sponge blasting a smoke damaged wind turbine. It has 4 sections, approximately 17 metres in each, and stands about 70 metres off the ground. The scope was to blast off all the soot and smoke off the existing coating and leave it intact. For it was not burnt or damaged, but if they washed it, it would actually stain the coating and they would have to then blast it anyway. Water was considered for the option. Again, the clean-up and staining would lead them to have to pre-blast the substrate to allow a coating to go over the top. So SpongeJet was selected for doing this process. The project size was some 1,000 square metres from the top to the bottom. Every area had to be blast clean in readiness for the overcoating process. As you can see, it was quite bad inside. Throughout each section, there was extreme smoke damage that had bedded deep into the coating surface. Scaffold was erected using 48 sections from the bottom to the top. The picture to the left shows where the coating had been whip brushed or blast blasted, and on the right it's the completed section ready for the coating to go over the top. The contaminants were removed as the whip blast profiled and etched the remainder of the coating, ready for the top coats to be applied. On the right is the finished project. Also, both sides of the floor sections required blasting for a new coating to be applied. I quoted this job at 2.2 kilos per square metre. As it was only a sweep blast, it had no metal to be exposed. The finished job consumed 625 kilograms. That worked out to only be 1.6 kilos consumed per square metre. 15 days were allocated to blast. The project was finished in 9 days, and that worked out to 111 square metres per day. That's 18.5 square metres per hour for a 6-hour blast day. That completes these some of the best case studies on the turbine applications. We'll go through and have a look at a few other processes that happen inside power plants. Water box refurbishment in the power station, and this is for Loy Yang B, project 920. Wayne Vincent, the contractor, was asked to quote on sponge blasting and removing a vinyl ester coating off the internals of the water box. I believe it was the Coricoat product that we were removing, and all the other water boxes in the plant have a Belzona coating on them. And I think this was the last one to be converted over to Belzona. The before and after shots, again, it's very important to have these shots to assist us in building a case study. The finished blasted substrate, and it's ready for Belzona coating. A blend of media was used on this, which we used 16 grit and 30 grit at a 50-50. It was believed that the vinyl ester product was exceptionally hard to remove. As it turns out, it was not too bad. But they did lose some of the media into the conduit pipe, and the consumption rate worked out to be 5.4 kilos per square metre. And they had a working mix left over at the same time, which Wayne, or the contractor, stored to use the media on their very next application. Project 802. This project was completed by Levi in Townsville and performed at the Pioneer Sugar Mill. It was a tube face that had to be blasted and coated. It was blasted and coated 12 months prior. Upon inspection, they'd found that the coating applied 12 months before was non-existent. Soda blasting was a process that they used to remove the coating and profile the surface up, and it didn't provide sufficient angular key for the coating to survive over that period of time. The tube face was being unprotected for a long period of time, and it suffered from severe pitting. Silver 16 was used to blast the substrate, 11 bags in total. That was 199 kilos to blast 25 square metres. That was 7.96 kilograms per metre squared. There was up to 3 mil pitting on the tube face, and the tubes didn't need plugging, and that saved valuable time. The before and after shots. The complete job, all buttoned up, the client was very happy with the performance of the whole process. There was no mess. It was an easy job to perform. Project 698, a small case study of the discharge condenser suffering from wear and erosion of the existing coating system. Media used on this project was silver 16. There were no volumes given, so I can't do some calculation for you. But the unit usually gets transported off-site, and they perform a and this time they perform the refurbishment on-site and in situ. They finished 1.5 or a day and a half earlier than they would normally do, thus saving in time and money. Project 903. This is CW pipes external to a cooling water system. The pipes presented severe corrosion, D-grade rust contamination at many points along the pipework, and appropriate surface treatment for coating was required. Petrobras detected a risk of mechanical treatment, which is hand grinding and under an ST3 standard, would potentially remove too much metal and could break down the pipes due to the fact that it was extreme corrosion and it was apparent to more than 70% of the wall thickness. This service had to be done whilst the cooling tower was in operation. Petrobras requested SpongeJet Global, the contractor, to perform the SpongeJet abrasive blasting on this particular project. Not only the large inlet and return water pipes were showing signs of severe corrosion, smaller pipework suffered from the same issue. Stirrups, saddles, cleats were all suffering from the same aggressive corrosion. The main water feed and return pipelines also suffered from aggressive corrosion and blistering. The project was performed while the pipeline was in operation. The inset picture is the actual blasting of the pipeline, exposing the aggressive pitting. The sponge media used was silver 30, producing sufficient profile to support the application of a high-build epoxy coating. Pictures of a work in progress, the scaffold around, the pipework, all showcasing the finished product. Project 868. Repair of cooling tower inlet water pipelines. Although this was in a sugar mill, a power plant inlet and return water pipes suffer from the same issues. Entrained solids breaking down the steel or concrete pipelines combined with corrosion and concrete spalling create problems with the integrity in any of these type of industries. This particular set of pipes were buried 8 metres underground, positioned beside a river meant that the pipes were sitting in the water table and suffering from ingress of contaminated water. The scope called for the repair and rebuild of the internals of the pipes, which were both metal and concrete. It required the rebuild of the concrete with Belzona Magma quartz. Rebuilding of bolt fillers were used, and they were all Belzona, bringing the integrity back to its original condition. In some areas there was necessary to bond in steel plates, and other areas required simple repairs. The before and after shots of the splitter outlet. Once again, it's always good to have the before and afters. There were issues with the exposed Rio in the concrete pipe. It had eroded away. It was blasted back to the original state to an SA3, then rebuilt with Belzona quartz and overcoated with 1341. The client was very happy to see the finished result, and the pipeline was inspected 1 year later, and found that there was no damage to the repairs and maintained its design integrity. Now we'll look at some steel columns and concrete and other case studies. Project 779. The purpose of showing this case study is for the blasting performance on concrete. Although the project was to remove low-level radiation off the surface of the concrete, it also removed the coating at the same time, which is what we do as far as the process is concerned. It lightly abraded the surface and removed the contaminants. The substrate was tested and there was no remaining radiation. Although it was contained in the medium, it doesn't redeposit the contaminants back to the substrate in the same process and principles as a soluble chloride removal, so that means it can be blasted, reused without redepositing back to the substrate. The same process continued in the facility's pump house, where the walls and ceilings and the coatings were removed, including all the contaminants. I-beams, steel roof and concrete walls were prepared. And I've just taken this additional tile. This hasn't got anything to do with that case study, but just another roof sections and walls that have been blasted. This is about the Saraji mine in Queensland. Andrew Hill of Blastoff Marine trained the on-site contractors to blast with sponge jet to rip up the internals of the workshops and buildings and prepare the walls and roof sections for overcoating. We have the finished photos, and I'm in the middle of building a case study for that now, but they're achieving 140 square metres out of 400 HP per day, using 220 grit for the surface preparation. Project 902, the largest Australian power company. The towers were suffering from corrosion on the galvanising that were 20 years old. They asked us to prepare a specification to blast the existing galvanising and to remove the visible corrosion and offer some guidance. There are 4 stages to corrosion on towers that have been identified. Phase 1 is a coffee stain. Rust is cosmetic, not structural, and 5% rust. Rust appears on the edges of the bolts and approximately 1 to 2 mils of galvanising remains. Phase 2, abrasive rust. Rust appears on bolts, edges and the horizontal flat areas. Rust falls off on touch. Phase 3, extensive abrasive rust. And Phase 4, tower failures. They're the 4 stages that have been identified. This is a job that we performed through the trials. They went to extremes to encapsulate the tower. Mostly was to be able to contain the sponge media as much as possible. They were using very expensive chute that was able to send the media directly down to the recycler. I must admit I was pretty impressed with it, but not very cost effective. I've just chucked it in there. Even the locals were worried about what the fuss was all about. Recycler was set up at the base of the tower. 100 HP was quite suitable for the blasting process. We blasted at 35 psi. Vertical blasting was performed up to 65 metres away from equipment. The tower consisted of 180 square metres and it's 65 metres high. The media used was silver 60 and the consumed volume of the media was 43 bags. It calculated to 580 kilos to blast 180 square metres. That calculated back to 3.2 kilos per square metre. Project 799, transmission structures and the substation attached to the power station. All of the work on these towers were performed while the unit was live, and they did design an easy containment box, and it was constructed around the towers and it could be elevated as required. The galvanising was at stage 3, shown in the matrix earlier, which was a heavy flaking rust. They used silver 30 to perform this application blasting on the galvanising. For transmission towers, I recommend that silver 60 or even less, an 80 grit, because we don't need to remove the galvanising, just remove the condition on the outside. They used 7 bags per tower. They calculated out to 127 kilograms. There was no job details given to me as what the meterage was, so I can't give you some calculations on that. They did use a 100 HP and a recycler. The scope was to remove the galvanising and recoat with a zinc-rich epoxy. Now we'll look at some outer structures. Project 904, a huge project in Brazil where the scope was to blast the connection and intersection points of the stadium structure. All the towers, verandas and sections were removed and brought down to ground so that they could be blasted out of a cherry picker, and the ground was covered with huge tarps not to contaminate the ground. Shown here is a series of pictures so it can offer you some size of the actual project itself. The media used was silver 30, and the project consumed 240 bags. That's 4,344 kilos, around 4.3 tonne. And if the consumption rate was based on our matrix, which we usually use 3.6 kilograms per square metre, the job total square metres to be blasted would be around 1,200 square metres. Project 856. Structural steel suffering from corrosion in an amusement park. The job scope was to blast the superstructure and structural bases. The work had to be performed outside the park's normal operating hours. They needed a 2.5 level of cleanliness and required a 70 to 80 micron profile. Hand tools were considered for this particular job, but they could not get into the intricate parts of the steel structures with hand tooling, and therefore blasting process was the best way forward. Some of the steel sections showed only minor corrosion. A simple fixed tarp aided in the recovery process. The client had used mechanical and power tools in the first instance, and then specified sponge as the process went along. They'd only done one leg before they went across to sponge jet. They used or consumed 15 bags of silver 30, that's approximately 270 kilos. The square metres weren't disclosed, but given that 3.6 kilos per square metre is our guide, that equates to about 75 square metres in total. And they also used a 100 HP and a recycler. Project 781. Coal separator and a coal-fired power station suffering from high abrasion wear. Welding and welding plates in was a temporary fix, and they found that it wouldn't last all that long either. The contractor put forward laser blasting with sponge jet and coating with a high build ceramic-based coating. This included the outlets and passage pipes, including the feed and pulverizer sections. The client looked at replacing costs against the refurbishment costs and agreed to see the job through with blasting the sponge jet in conjunction with coating and rebuilding the damaged sections. Why are we showing this process? The pulverizers suffer from high abrasion. Most power stations use high build products like our quartz products. On the inlets and chutes, the diverters, the diverter valves, and they all need surface preparation. After the unit had been put back into service, they checked it after 26,000 hours, checked it again after 40,000 hours, and the coating had held up. So there's a good walk-up application for most coal-fired power stations for high-build epoxy coatings. The power station now uses the same process on all high abrasion components. Now we'll just look at a couple of tank jobs. Project 783, one of the largest coal mines in the world. This is the Cerrejón mine in Colombia. Stores and houses its own fuel. and this case study is about removing a failed coating system off the externals of the diesel storage tank. Consisting of 1,800 square metres, this tank project needed to remove the existing paint system and have an SA3 level of cleanliness. Due to the location of the tank, there could be no dust floating across the plant. SpongeJet was selected and a methodology of blasting off a cherry picker and shade cloth was adopted quite successfully. I presented this case study to AGC for the Melville Island diesel storage tank project, and it was this case study that helped me get the project across the line. Using 2x400 feed units, they performed 128 square metres per day. That's 64 square metres per nozzle per day, and that related to a 6-hour blast day. They were producing 10.6 square metres per hour. If they blasted an 8-hour day, which they haven't determined the hours in the case study, the blast time per day they would have achieved 8 square metres per hour. The consumption total was 4,887 kilos. That's 270 bags of 30 grit. And that calculates back to 2.71 kilos per square metre. The tank top was also prepared. Media fell to the ground for easy collection while blasting off the cherry picker. The blasting of the tank was completed. They finished tank number 1, and there was another tank project followed this process. It was the same size, same type of storage tank, and they went through the same process on tank 2. Project 680, refurbishment of a condensate tank in a power plant. The aggressive environment of the condensate tank accelerated the coating breakdown, and it had to be removed. The scope called for an SA3 and a profile of 75 micron finish. The internal environment meant that the workers enjoyed minimal exposure to airborne contaminants, and safety was paramount on the job. The personnel would blast all day and collect once at the end of the shift, all for recycling. There were no square metres given in this project, so I'm unable to give you some rates, but as you can see, there's a fair amount of square metres involved in the internals of the tank. Stripe coating and a complete spray and overcoat was employed to complete this project. We've got many more tank applications in our case study format. We can share these, some of these with you in future webinars. We'll move on to concrete buns, floors, and maybe some bitumen. Project 826, a removal of failed coating. That's 30 years old. It was an epoxy coating, and to remove it off concrete. The specification was achieved. The specification to achieve a CSP5 concrete surface preparation, and this is derived from the concrete standards. So CSP is concrete surface preparation standards of the scale. The surface prep was performed by SpongeJet, preparing the substrate to that standard and applying a new protected coating over to prepare the surface. This application led to the contractors doing other applications inside the power plant, one of them being Project 827, a flocculation tank. It was a cleaning process and cleaning and refurbishment of that tank. The objective was to remove a coating off the concrete and remove the flocculation tank. Again, the scope called for a CSP5 surface preparation. The media used was silver 80, and the stated consumption rate was 1.8 kilograms per square metre. The reason we're showing these case studies is to show you that the ease of surface preparation for concrete buns, floors, walls, in fact any concrete surface that needs a coating is easily prepared with SpongeJet. Project 907, the use of sponge blasting in a domestic environment, buildings and structures. Our mindset should be that concrete is not a hard process, or concrete blasting is not a hard process to perform. The production achieved can range between 8 square metres to 40 square metres per hour, and this is determined entirely by the scope of works, what you've got to remove, and the consistency of the concrete itself. The application was to remove the paint coatings from 120 concrete balconies on a domestic block of units. The reason for selecting sponge was the lack of airborne contaminants, and dust would have been an issue with those units. The media used was Silver 60. Reclaiming was performed off large plastic sheeting that they had on the ground, and the damaged balconies could then be restored back to their original state. I will supply to you all a visual chart comparative for the surface preparation requirements for coating, skimming and rebuilding of concrete. Note that all CSP surface preparations can be achieved by sponge blasting from CSP1 right through to CSP9. At the end of the course, we'll also give you a matrix of the reasons for that coating surface or surface preparation. The next few case studies will be about other applications that are performed in power plants. Project 828, a generation vessel, or an AKA, it's a condensate polisher. It had a rubber lining in it, and it was removed with SpongeJet, and it was to remove an adhesive compound that was left on the substrate and to prepare it for a new coating on the inside. Normally they would use copper slag on this particular application, which they would use 9,000 pounds on 3 vessels. That's 3,000 pounds per vessel, or 1,361 kilograms of copper slag. Silver sponge media 16 was used in its place, and this tile shows the breakdown and the costs, and more importantly the saving. This tile does, I apologise about that. The overall saving on this project was significant. That's a whopping 22-to-1 ratio as far as the savings are concerned between doing it with copper slag, and I will put copper slag in the same bracket as garnet. The harder the surface is to remove, the more benefit SpongeJet becomes. Garnet will break down a lot quicker than the media or than the aluminium oxide. Pumps, hydro and other. On-site application work, this is Project 808, preparing a wear ring that supports the top and the bottom of the casings that are bolted together. We're suffering from cavitation damage, and they would have to continue to perform this process on a regular basis as a temporary repair until they could replace it in a major outage. This application was made more difficult when the separations of the wear ring could only be lifted to 32 millimetres, leaving very little room to blast directly onto the substrate to repair the cavitation damage. A special deflection nozzle was used where it could perform the blasting on the top and the bottom of the cavity at the same time. This project was not about production or cost, but it was a solution to a problem solved by using sponge. Project 869, and this is the last one, it'll only take another minute. It's in a coal-fired power station. It's a circulation pump and associated parts. The volute, diffuser and the impeller were all blasted on site. It weighs over 10 tonnes and it's usually transported off-site to perform the repairs, the blasting and the recoating. The client decided to perform the application on site. The circulation pump square meterage totaled 46 square metres. It required a blast cleanliness level of an SA3, a near white blast, and the other parts only needed a whip or an existing, a whip up of the existing coating, I should say. Only 5 bags of silver 16 were used in the blasting process, and that calculated that to 90 kilos or 90.5 kilos to abrade 46 square metres. That worked out as a 1.967 kilos per square metre. Before and after blasting shots of the impeller. The volute is positioned at the bottom of the lift section, 21 metres down underground. All of the blasting for this process was performed in situ. And again, we see the before and after blasting shots. The outcome was was a very satisfied client for this particular power plant. That's all. So today's webinar, we've covered many aspects of the power industry, and I hope it's been informative. And we'll now open up the microphones to take any questions that you might have.